Hello guys, now we are in the next chapter, that is electrochemistry, your chapter number 3 of your class 12. Okay, so as we know that electrochemistry is a branch of chemistry that deals with the relation between electrical energy and chemical energy, moreover their interconversion. Okay, there is some kind of relation between magnetic energy or magnetic field and electric field. And we know that we can convert magnetism into electricity and electricity into magnetism. Like that, we can convert electrical energy into chemical energy or chemical energy into electrical energy through different types of process. Okay, and what are the process and how we can convert this into other is all are discussing in this chapter. Okay, so this is something which discuss the relation between electrical energy and chemical energy, moreover their interconversion. Okay, so mainly there are 5 sections in this chapter. Your first section, that is conduction. Your first section is conduction, and the second section, that is electrolysis. Second section is electrolysis. And the third section is galvanic cell. Galvanic cell. And the fourth section, that is battery and corrosion. Battery and corrosion. Moreover, the fifth or the last one, that is titration. We have redox titration and conductometric titration here. Ready? So titration which related with the conductivity, which means a relation with the electrochemistry, and moreover a titration which is in relation with the equivalence concept or redox concept. We know that, or we are already discussed the chapter redox reaction. So the last topic is titration. So these all are the important topics in your chapter number 3, electrochemistry. Okay, so let's discuss one by one. Ready? Now, your first topic, that is conduction. Conduction. And this chapter belongs to physical chemistry. So, we have plenty of problems, different types of problems here. Okay? We will discuss. Ready? So, the first one, conduction. The first topic, that is conduction. You know that conduction is a phenomenon of passage of, or the passage of electricity, right? Fine. So, conduction means it is the phenomenon of passage of electricity through substance. Okay, we are given with some substance, and if the substance is able to allow the passage of, or if the substance is allow the passage of electricity, then we said it as a conductor. Ready? And the process, the phenomenon which taking place is said to be conduction. Ready? There are basically 2 types of conduction. Okay, so your conduction can be classified into 2. There are 2 types of conduction, and the first one is metallic conduction. Metallic conduction, and the second one is electrolytic conduction. Electrolytic conduction. So there are 2 types of conduction, metallic conduction and electrolytic conduction. For your metallic conduction, you simply assume a metallic wire, a piece of iron or a metallic wire, in which we have plenty of free electrons, right? Yeah. And the free electrons and kernels, you know the term kernel? The free electrons and kernel in this metal crystals are which is in a metallic bonding, right? What do you mean by kernel? Kernel is nothing but it is the part of your atom other than valence electron. For a metal atom, usually the valence electrons are loosely bonded and they simply get outside from the metal atom. Okay, so the valence electrons are like this. In a metal, if you are considering a metal, we have a lot of atoms in which its valence electrons are in which its valence electrons are get outside like this. Okay, ready? So the remaining part, the part of atom, something other than valence electron, what we called as kernels. These all are said to be kernels. Kernels. Nucleus plus inner shell electrons. Nucleus plus inner shell, what we call as kernels. And these all are the valence electron of that metal. Valence electrons are completely free now. Okay. So these valence electrons can flow through the metal crystal, which cause the conduction. Ready? And there will be an attraction between, there will be a force of attraction between these kernels and valence electron. That what we called as metallic bonding. Ready? Fine. So simply in the case of a metallic conductor, you assume a piece of metal in which kernels are the constituent particles and valence electrons are loosely bounded, also means which is get free. Okay. And now the next, that is electrolytic conduction. We have a molten form of NaCl in which Na plus and Cl minus ions are completely ionized, right? If you have a molten form of NaCl in which the positive negative, if you have a molten form of an electrolyte, the electrolyte may dissociate into cation as well as anion. Okay, and these ions, these positive negative ions are responsible for the conduction of this electrolyte. Okay, keep it on mind. Now we can compare metallic conduction and electrolytic conduction with some criteria. The first one, the charge carriers. For a conduction, for a body to conduct, there will be some charge carriers to flow. Okay, there may be a flow of charge carriers for a body to conduct. Okay, in metallic conductor, the charge carriers are, it is clear that they are free electrons. Okay, so simply here in the case of metallic conductors, charge carriers are electrons, whereas in the case of electrolytic conductor, the charge carriers are positive negative ions, right? So in the electrolytic conductor, the charge carriers are ions. Okay, in metallic conduction, no matter is transporting. Okay, no matter is moving, right? There is you know that the matter means this atom or this main part, this still remains in rest, where the electrons are moving, right? So if the matter is iron, the iron atoms are not moving, agreed. But in the case of electrolytic conduction, if you have NaCl, the matter Na plus and Cl minus, the ions which are readily moving, right? So the next point is about the moving of matter. Okay, so no matter transferring in the case of metallic conductor, but here matter is transferring. Ready? Okay. And we know that if a iron body conduct electricity, there is no chemical change for your iron, right? Yes. But we have, if we have NaCl, in the molten state it exists as NaCl, but when it is in in the solid state it exists as NaCl, but when you bring it into a molten state, it becomes Na plus and Cl minus. Whenever the ions get free, then only they can show conduction. Okay, so there is a chemical decomposition of NaCl to Na plus and Cl minus. Then only the ions are formed. Then only the conduction is observed. Okay, so in the case of ionic conductance, conduction through a chemical decomposition. But in the case of your In the case of your metallic conduction, there is no chemical change. No chemical change in conduction. So in the time of conduction, there is no chemical change for your metallic conductor. But if here conduct through a chemical decomposition. Conduct through a chemical decomposition. So here the NaCl chemically or the electrolyte chemically dissociated into its component ions. Okay. So chemical decomposition. Ready. So that is the next comparison point. Since the charge carriers of metallic conductor are electrons, this is also known as electronic conduction. What? Electronic conduction. Here the charge carriers are ions. The electrolytic conduction is also known as ionic conduction. Okay, so metallic conduction, otherwise known as electronic conduction, whereas electrolytic conduction, otherwise known as ionic conduction. Okay, fine. So moving to the next point. If temperature increases here, in the case of metallic crystal or metallic solid, if temperature is raised, then the vibration of these constituent particles, what we call as kernels, right? This vibration may increase. As temperature increases, in the case of a metallic conductor, the constituent kernels get vibrated. If they get vibrated, means the electron is difficult to move from one end to another end. So the flow of charge carrier is restricted, which means resistance increases. As temperature increases, vibration of kernels increases. So the flow of electrons restricted, which means resistance to the flow of charge carriers increases. So as temperature increases, resistance increases. Okay. So as temperature increases, a vibration of kernels increases. What? Vibration of kernels increases. Therefore, resistance increases. What do you mean by resistance? The opposition force to the flow of charge carriers. Whereas in the case of electrolyte, as we increase the temperature, what happens? There may be an attraction between the oppositely charged ion if they are if still they are dissociated. Okay, we know that NaCl is dissociated into Na plus and Cl minus, but this still a negatively charged ion and this a positively charged ion. There may be an attraction, what we call as interionic attraction. As we increase the temperature, this interionic attraction decreases, right? The ion to ion attraction decreases, which means the ions get more free. If the ions get more free, means they can move. The ions are the charge carriers, right? Yeah, they can move as based on its wish. Okay, so which increases its conductivity, right? So ions are ions can move with full of freedom if you increase the temperature, because interionic attraction decreases. If the charge carriers, which means your ions are having greater freedom, means the restriction decreases, which means the resistance decreases as we increase the temperature. Okay, so here in the case of electrolytic conduction, if temperature increases, what? If temperature increases, what happens? The counter effect is interionic attraction. Interionic attraction that decreases. The attraction between two oppositely charged ions decreases. If the attraction decreases, means ions get more free, which means resistance also decreases. Resistance also decreases. Okay, these all are the basic difference between your metallic conduction and electrolytic conduction. Okay, so keep it in mind. Now we are discussing the whole idea about your electrolytic conduction, and about your metallic conduction it may be discussed in your chapter number 3 of physics, current electricity. Okay, so now we can enter to the term electrolytic conduction. Ready? So in conduction, now our topic is electrolytic conduction. So for electrolytic conduction, we can discuss, our dimension is, first of all, we can define some terms in electrolytic conduction. So there are some terms which you have to know in electrolytic conduction, okay, that we are discussing. Ready? Like your resistance, resistivity, conductance, conductivity, molar conductance, equivalent conductance, like that. Okay. So listen, first of all, you have to know that we are discussing about the conduction of electrolyte, not a conduction of a metallic wire. This is not the dimension. This is a metallic wire. So this is not the case. We are simply discussing, we have a electrolytic tank, where the tank in which electrolyte is filled. Electrolyte means means a positive, negative, cationic, anionic part of your electrolyte. Okay. So if you consider a electrolytic tank, we can observe there are a lot of positive, negative ions. Ready? So this is our boundary. This is our boundary. Here we are discussing, or here we are defining some terms. So first of all, keep it in mind that we are not discussing something about a metallic wire. We are discussing the conduction of electrolyte which is in a electrolytic tank. Okay, fine. Ready? Listen. So in that dimension, we want to define some terms. Your first term, first of all, you have to know that like what? Like metallic conduction. Like metallic conduction in electrolytic conduction also obey Ohm's law. In your electrolytic conduction, there also obey Ohm's law. Okay, like your metallic conduction, in your electrolytic conduction, there also we can observe the Ohm's law. Okay, so based on Ohm's law, you know what is Ohm's law? I think you are familiar with that. Okay, potential difference across any conductor is directly proportional to the current flowing through it. Okay, so if you are taking the ratio V by I, we obtain a constant what we call as resistance. Fine. So that is our first term. That's our first term, resistance. What is the term? Resistance. And resistance symbolically represented using the letter R. Okay. And it is clear that resistance of a conductor is directly proportional to length of conductor. Length of conductor. And the resistance is inversely proportional to area. Area of conductor. This doesn't mean that we have a piece of wire with a L length and a area cross section. It simply means that we have an electrolyte in its tank. Electrolyte in its tank. So if you are considering a volume, a particular volume in this tank, we are considering a particular volume in this tank. Okay. So we are measuring the conduction in that particular region, where the length of this conductor be L and the area of this conductor, area where the electrolyte enclosed be A. So that is the meaning of your L and A. Ready? Fine. So as in the your means just like your Ohm's law in a metallic wire, here also it obeys Ohm's law. That's why I write this as R proportional to length of conductor and R proportional to 1 by area of conductor. So L means you have to know. L means the length of that particular dimension where electrolyte is enclosed, and A is the area of that particular region. Okay. So here clubbing this one, R will be proportional to L by A, or R is equal to a constant rho L by A. So R is equal to a constant rho L by A. Okay, I'll describe about rho because that is our next term, resistivity. You know that. Okay. So you simply know that R equal rho L by A, and the unit of the resistance is ohm. Unit of resistance is ohm. Ready? So we got R equal to rho L by A with a unit ohm. Okay, our unit is ohm. Ready? Fine. So the next, listen. The next, this is a first term, resistance. Moving to the next term. Your next term is resistivity. What is the term? Resistivity. Resistivity. Okay, resistivity or rho. Resistivity means rho. What do you mean by resistivity? Okay, or simply, what is the expression for resistivity? Resistivity, or it is otherwise known as specific resistance. Specific resistance. Okay, I'll define the resistivity. Before that, what is the expression for resistivity? We know that R equal to rho L by A, therefore rho equal to Ri by L. Rho equal to Ri by L. This is the expression for your resistance. Okay, so unit of resistance will be unit of resistivity. This is the expression for resistivity. Your resistivity is rho. Okay, and rho equal to Ri by L, where R is resistance. So the unit of resistivity will be unit of resistance into unit of area divided by unit of length. Okay, so unit of area, length square, unit of length. So length square and length get cancelled. So the final will be ohm meter or ohm centimeter. Here ohm centimeter is also taking. Okay, because we are simply considering a small dimension. So centimeter dimension is enough here. Okay, so either the unit may be in ohm meter, or we can use ohm centimeter also. Ready? Keep it in mind. Fine. So from this expression, let me do something. If the area of my conductor is 1 centimeter square. 1 centimeter square. I told you that here centimeter dimension is more comfortable than meter dimension. Okay, so area of the conductor is 1 centimeter square, and the length, that particular length of your conductor is 1 centimeter. Then what happens to rho? Rho will be equal to R. So it is clear that your resistivity is equal to resistance. So it is clear that resistivity, it is the resistance. So what is resistivity? It is the resistance. So resistivity is the resistance. At what time? If the conductor have one centimeter square area and 1 centimeter length. If you have 1 centimeter square area and 1 centimeter length, which means that the volume of conductor is 1 centimeter cube, right? If you have 1 centimeter square area and 1 centimeter length, means we know that area into length will be volume. So the volume, which means that volume of the particular case is 1 centimeter cube. So if the volume A equal to 1 centimeter square or L equal to 1 centimeter, means that volume equal to 1 centimeter cube. So it is clear that if the volume of your conductor is 1 centimeter cube, then the resistivity will be equal to resistance. Resistivity will be equal to resistance. That is the idea. So resistivity, it is the resistance. Resistivity, it is the resistance when resistance of a conductor with a unit of 1 centimeter cube volume. 1 centimeter cube volume. Okay. So if you have an electrolytic tank in which we are simply considering a cube of volume of 1 centimeter cube, then what is the resistance of this 1 centimeter? This is the actual dimension in which we have a cube of volume with 1 centimeter cube. Then what is the resistance of this cubical 1 centimeter cube volume? That is the resistivity. So resistivity is a specific resistance. It is a well specified resistance. What is that specified condition? Your volume of the conductor should be 1 centimeter cube. If the volume of the conductor is a specified one, which means 1 centimeter cube, then what is the resistance? That will be the resistivity. That is that's why resistivity is otherwise known as specific resistance. So what is resistivity? It is a resistance of a conductor having 1 centimeter cube volume. Okay. So no need to stick on in this topic more and more time. Okay. No need of spending more and more time in this topic. Okay, we are moving to the next category. That is, the category is we discussed about resistance, resistivity. So it is clear that our next term will be conductance. What it is? Conductance. Okay, we know that conductance is the easiness of flow of charge carriers, and your conductance in electrochemistry, it is represented using the letter G. Okay, so conductance is simply mathematically it is reciprocal of resistance. So what is a reciprocal of resistance? That is a conductance. So conductance G is the reciprocal of resistance, which means 1 by R. So conductance G is 1 by R. And we know that R equal to rho L by A. Rho L divided by A. Then what is 1 by R? A by rho L. So conductance G is equal to A by rho L. Ready? A by rho L. Then what will be the unit? Unit may be the 1 by the unit of resistance. 1 by ohm, which means ohm inverse. Like this, or in this fashion, ohm inverse. Or the ohm inverse, otherwise known as mho. Inverse of ohm. Inverse means this is ohm, so this will be the inverse. Mho. Ready? Or it is otherwise known as Siemens. What? Siemens, capital S. So the unit of conductance is 1 by ohm, which means ohm inverse, or otherwise known as mho, or otherwise known as Siemens. Okay, so this is conductance. Ready? So conductance is okay. Moving to next, conductivity. What? Conductivity. Conductivity represented by the letter kappa. This is the letter kappa. Kappa, it's a Greek letter kappa. So conductivity kappa. Ready? Conductivity will be if conductance is the reciprocal of resistance, then if conductance is the reciprocal of resistance, resistance. Similarly, conductivity will be the reciprocal of resistivity. So, what is conductivity? It is the reciprocal of resistivity. It is the reciprocal of resistivity. So, conductivity is the reciprocal of resistivity. That means your conductivity kappa will be equal to 1 by rho. What is rho? Ra by L. Then 1 by rho will be Ra by L. L by Ra. 1 by rho will be L by Ra. But this can be written as 1 by R into L by A. Listen here. L by Ra will be written in this form. 1 by R into L by A. What is 1 by R? That is G. 1 by R is G. What is G? Conductance. So here, so this is G into L by A. So G into L by A. So your conductivity kappa equal to 1 by the resistivity or L by Ra, or is equal to G into L by A. So what will be the unit? 1 by resistivity. So 1 by the unit of resistivity. We know that unit of resistivity is ohm inverse, ohm centimeter. So it's a reciprocal means ohm inverse, centimeter inverse, 1 by ohm centimeter, ohm inverse, centimeter inverse, or we can write ohm as Siemens, ohm inverse as Siemens, according to this one, okay? So Siemens, centimeter inverse, fine. Okay, fine. So let me define the conductivity like we defined the resistivity in the previous case. That is, if you have a conductor of length 1 centimeter and area 1 centimeter square, which implies that we have a conductor with the volume 1 centimeter cube. Then what happens to conductivity? Conductivity equal to G into 1 by 1. G into 1 by 1. So conductivity is equal to G. So conductivity is a conductance. Conductivity is a conductance. So that's why conductivity is otherwise known as specific conductance. Specific conductance. So your conductivity is otherwise known as specific conductance. Or we can define the conductivity as conductivity is the conductance. So conductivity, it is the conductance of what? Conductivity is the conductance. Conductivity is actually conductance of what? Conductance of electrolyte of volume 1 centimeter cube. If we have a electrolyte of volume 1 centimeter cube, like, then the kappa will be equal to G, which means conductivity will be equal to conductance. That's why the conductivity is otherwise known as specific conductance. Specific conductance. So now it is clear that all the four terms. What are the terms? Resistance, resistivity, conductance, conductivity. Okay, there is one more term, that is cell constant. The term is cell constant. So let me connect these all with the cell constant. Let me connect these all with the cell constant. Cell constant is important. Okay, now we can look into the cell constant. Actually, if you have an unknown solution, I have an unknown solution A, B, C, like that. Unknown electrolyte with an unknown resistance A, unknown electrolyte with an unknown resistance B, unknown electrolyte with an unknown resistance C. Then actually I can measure the resistance of each solution using a special apparatus called conductivity cell. Conductivity cell. So let me discuss about that. What? How we can measure the resistance of solution using conductivity cell. Okay, I'll give you a clear picture about it. Okay, then we can connect something with our discussed term, means your conductivity resistance, like that. Okay, so the topic is measurement of resistance in conductivity cell. Okay, put it as a not, N-O-T, not. Okay, measurement of resistance in a conductivity cell. A conductivity cell is something like, I'm not good in drawing, okay, so you simply adjust this, okay, something like this. Ready? We have 2 electrodes here, 2 electrodes here, okay, and the distance between these 2 electrodes simply defined as L. We have 2 parallel electrodes and the distance between these 2 electrodes is L, and the electrolyte is enclosed in it. So the area where electrolyte is enclosed will be equal to the area of that electrode. Area where the electrolyte will area where the electrolyte is enclosed will be equal to the area of that electrode. Ready? Fine. And this is a setup. Simply this is a setup, or we can draw it in like this in fashion. These all are 2 different types of conductivity cell. Okay. Here is your electrolyte, and the distance between these 2 electrodes is L, and the area of this electrode is A. Okay. Then for a conductivity cell, if you have a conductivity cell, then for every conductivity cell, for every typical conductivity cell, there will be a ratio. That the ratio means distance between, the ratio of L by A. The ratio is ratio between length to the area. Length means that is the distance between that parallel electrodes, and A means the area of that electrode. That ratio will be a constant for every conductivity cell. For every conductivity cell. That doesn't mean that all conductivity cell have same L by A value. It doesn't mean like that, okay? I have two different conductivity cell. Then for that typical conductivity cell, its L by A is a constant. For another typical conductivity cell, its L by A is a constant. Always it is a constant. If I am doing experiment of several times, say 1,000 times I am doing experiment with this particular conductivity cell, in the 1,000 times its L by A remains a constant. So for a particular conductivity cell, its distance between parallel electrodes and area of cross section of that electrode is a constant. That means L by A is a constant, and that typical constant which is defined as cell constant. Cell constant. Okay, but it is difficult to measure L by A. It is very difficult to measure the L by A. Okay, so we can calculate. Now look into here carefully. We know that what is L by A? Distance between parallel electrodes and A, but it is very difficult to measure L and A. Okay, I think the measurement is required for only once. If we know the L by A, always the L by A is a constant. Okay, but it is very difficult to measure L by A. So how can we calculate the value of L by A? It is very important. If I get the value of L by A, then it is enough for the whole life of that conductivity cell, right? Yeah. So how can we calculate that L by A? So we can calculate L by A by filling KCl solution. That is important. KCl solution or KCl electrolyte in conductivity cell. In conductivity cell. Okay, so you simply fill KCl solution in conductivity cell. And what is the advantage of KCl solution? KCl solution have an advantage, that is its conductivity known at different concentration. It is a standard solution, which means that at any concentration its conductivities are known. So first of all, you simply fill KCl solution in this. Okay, you simply fill KCl solution here. For what? To measure the L by A value. And we know the conductivity kappa of KCl solution. Okay, if I know the conductivity kappa of KCl solution, then if I am able to multiply the resistance of that solution, then I will get the value of L by A, right? Yeah. How it become like that? We know that kappa equal to 1 by R L by A, right? This is already defined. If you are crossing R to here, then conductivity times of resistance will be equal to L by A. That L by A is already set that it is cell constant. And your cell constant, which is represented using the letter G star. G star, okay? So L by A, which is represented using the letter G star. So G star is equal to L by A. Okay, what will be the unit of that L by A? L by A will be centimeter inverse or meter inverse. Okay, fine, leave it there. So it is very difficult to calculate or find out the value of L and A. Okay, then how we can find the value of L by A means, but there is an advantage. Once we find the value of L by A, then it is enough for whole time. Ready? So for a conductivity cell, how can we find out the value of L by A for a first time? For that, we can fill the conductivity cell using KCl electrolyte. What is the advantage of KCl electrolyte? Its conductivity is already known. So for a KCl electrolyte, its conductivity is known. Ready? And if you know the resistance of that particular KCl solution, then we will get L by A, right? According to this equation. So conductivity is already known. So how can we find the resistance? For finding the resistance of this solution, we can simply connect this with the Wheatstone bridge. You can simply connect this with the Wheatstone bridge. I think you are familiar with the Wheatstone bridge. Okay, and from the balanced condition of your Wheatstone bridge, when in balanced condition, if the Wheatstone bridge is in balanced condition, we can find resistance RKCl, and now we able to get, or now we obtain the values of conductivity of KCl and resistance of that particular KCl solution. So multiplying these two, we obtain L by A of that conductivity cell. So this is how cell constant measured. Okay, now I got cell constant. Then how can I find? How can I find the conductivity? Once I get the cell constant, conductivity of any solution, will be equal to resistance. 1 by the resistance into cell constant. Okay, so once I know, or once I find the cell constant, what is L by A? This is cell constant. Once I find the cell constant, I can simply substitute the value of G star here. And now if I remove this KCl from this one, and I fill a solution A, and I want to find its conductivity. Simply I just filled a solution A in the very same conductivity cell, and I want to find what? Its resistance. Conductivity. So can I find the conductivity? Conductivity, we know that conductivity kappa equal to 1 by R into L by A, or 1 by R into G star. This is the equation, right? This is the equation for conductivity. So this is exactly written in the above. Okay, conductivity of any solution is equal to 1 by the resistance of solution. Okay, and how we can find the resistance of solution? You simply put that solution into the already defined conductivity cell, and now I simply put A here, and using Wheatstone bridge I can find the resistance, and I am simply substituting the resistance, and we already know that the value of what? We already know the value of G star. So simply multiply it with the G star. You obtain conductivity. So for any solution, we can easily find its conductivity if we know the resistance. Okay, so and the resistance can be measured with the help of Wheatstone bridge. Okay, so this is how resistance measured in a conductivity cell. If we know the resistance and moreover that a particular dimension L by A, I can find the conductivity. So for any electrolyte, our duty is to find resistance. If I know the resistance, already I know the G star, but there is a task. There is a task means first of all we want to find the G star of that particular cell by filling KCl solution, and this is described here. Ready? Once I know the G star, it is always remains a constant. So G star is fixed. Then we can place any electrolyte here, and with the help of Wheatstone bridge, we can find its resistance. Okay, so resistance, if I know the resistance, then the reciprocal of resistance into the already find out the G star which is already known to me. Simply multiply with the G star, then you obtain conductivity of any solution. And this is how the measurement actually proceeding. Okay, so I think you got idea about your conductivity cell constant and measurement of resistance. Once we know the resistance, we can easily find the conductivity. So I'll explain once again. Here in this section, I'm simply describing about how we can find the resistance of a resistance of any solution using conductivity cell. So conductivity cell is something like this apparatus, which means that we have two parallel electrodes, where the distance between the parallel electrode is L, and the area of cross section of that electrode is A. where electrolyte is enclosed. Okay, fine. And for any conductivity cell, the ratio of that L, the distance is always a constant and the area is always a constant. So L by A is a constant. And that constant for a conductivity cell is defined as cell constant, and it is symbolically represented by the letter G star. And G star will be equal to L by A, or the unit will be centimeter inverse or meter inverse. Okay, so there is a problem. It is not very easy to find G star, or it is very difficult to measure L and A to find G star. So in order to find G star, we are simply not finding L and A to find G star. We are finding L by A, the whole L by A, using conductivity times of resistance, using the relation conductivity times of resistance. Okay, so for that, we placed what? A KCl solution in that particular conductivity cell. What is the specialty of KCl solution? We know the conductivity of KCl solution. So K is okay, which means kappa is okay. Now, simply I want to find the resistance of that particular solution. How can I find the resistance? Simply connect that electrode with the Wheatstone bridge and simply proceed the working of your Wheatstone bridge. And you know that in balanced condition, Wheatstone bridge can provide the resistance of that unknown electrolyte. So once I know, conductivity is already know because it is KCl solution. That is a standard solution. And resistance is given from that Wheatstone bridge. Then if you are multiplying these two, you obtain the L by A ratio. It is very difficult to find L and A to find L by A. Now we simply find the ratio, whole ratio L by A, and it is defined as G star. So for this conductivity cell, G star is fixed. It is find out. It is already find out. Okay. By filling KCl in it. Ready? Now that KCl solution is removed. Now we can find conductivity of any solution if you know the resistance. So now I can fill NaCl solution in any kind of solution and simply find its resistance, and that resistance, reciprocal of that resistance into the cell constant, which is already found. You simply multiply, you obtain conductivity of that particular solution. So this is how conductivity is measured. For measuring conductivity, we want to find resistance. So this is a procedure. I think this is okay for you. Okay, simply you have to know this. Ready? So there are some relations you have to know. What are they? What are they? R equal to rho L by A. R equal to rho L by A. Okay? Rho equal to Ra by L. Rho equal to Ra by L. G equal to 1 by R equal to A by rho L. Kappa equal to 1 by rho equal to L by Ra, which is equal to GL by A, which is equal to G into G star, and G star equal to L by A, which is equal to kappa times of resistance. These all are the relations which is discussed up to this time. Okay. These all relations you have to by heart. Ready? Fine. Now we can move to the next type or next conduction, that is molar conductance and equivalent conductance. What are they? Molar conductance and equivalent conductance. So let me compare these two. Okay, so there are two more terms. What are they? Molar conductance and equivalent conductance. So the next fifth term is molar conductance. And that molar conductance is defined as lambda m. This is capital lambda. Okay, this you know small lambda, this you know capital lambda. Okay, molar conductance. Like, I think you are familiar with the molarity. You are familiar with the mole equivalence, molarity, normality, like that. Molar conductance and equivalent conductance. What are the terms? Molar conductance and equivalent conductance. and your equivalence conductance defined as lambda E. Lambda E. Ready? Fine. Now, I have a conductivity cell. Okay? And I'm simply filled 1 gram mole substance in that conductivity cell. Have a conductivity cell in which there are 2 parallel electrodes, and I filled 1 gram mole. 1 gram mole, or simply means 1 mole. 1 mole electrolyte here. So 1 mole NaCl here, which means that there are a lot of ions, right? Yeah. And what is the conductance offered by all ions in that 1 gram mole electrolyte? That is said to be molar conductance. If I placed a 1 mole electrolyte here, 1 gram mole electrolyte here, then the conductivity or the conductance offered by all ions in that 1 gram mole electrolyte, conductivity offered by all ions in that 1 gram mole electrolyte. I have 1 gram mole electrolyte there, and there are some lot of ions. And what is the conductivity, total conductivity of all ions in that 1 gram mole electrolyte? That is said to be molar conductance. Like if I have 1 gram equivalent electrolyte here, you know the difference between gram mole and gram equivalent. 1 gram equivalent electrolyte here. 1 gram equivalent electrolyte here. So 1 gram equivalent electrolyte also have a lot of ions. Then what is the conductance offered by that all ions in 1 gram equivalent? That is said to be equivalent conductivity. That is the difference. Okay. So what is molar conductance? It is the conductance offered by all ions in 1 mole or 1 gram mole electrolyte. 1 gram mole electrolyte. Like that. What is equivalent conductivity? It is also very same. It is the conductance offered by all ions in 1 gram equivalent electrolyte. In 1 gram equivalent electrolyte. So that is the difference. If 1 mole electrolyte in a conductivity cell, then what is the conductance offered by that all ions? That is said to be molar conductance. Whereas the very same time, if I have 1 equivalent electrolyte in that particular cell, then what is the conductance offered by all ions in that equivalence electrolyte, 1 gram equivalent electrolyte? That is defined as equivalent conductance. Okay. So listen here. Let me define relation between your molar conductance and specific conductance kappa. What do you mean by specific conductance? It is already defined. Kappa is already defined. It is a conductance of 1 cubic volume electrolyte, right? 1 centimeter cube conductance of 1 centimeter cube volume. But molar conductance means all ions, conductivity of all ions in 1 mole electrolyte. So there is a relation between lambda m and K. What the relation is that it is very easy. If kappa given in, if your kappa given in Siemens centimeter inverse, then the relation between lambda m and kappa is lambda m is equal to 1000. 1000 means 10 raised to 3 kappa divided by molarity. This is a relation. And unit will be Siemens centimeter square mole inverse. Unit of kappa will be, unit of lambda m will be Siemens centimeter square mole inverse. Very same time, if the kappa given in Siemens meter inverse, then lambda m expression have a small change. It will be 10 raised to minus 3. It is not 10 raised to 3. This one will be 10 raised to minus 3, which means the 1000 is upon kappa, okay, or in the denominator divided by molarity. This is the expression. The unit may change. Unit will be Siemens meter square mole inverse, where m is molarity. Okay, no need of derivation. You simply study this one. The very same manner, here also the relation. What? Relation between lambda m and, lambda E and kappa. What is the relation? Very same kind. If kappa given in Siemens centimeter inverse, if your kappa given in Siemens centimeter inverse, then lambda E equal to 10 raised to 3 kappa. Here lambda M equal to 10 raised to 3 kappa. Here lambda E equal to 10 raised to 3 kappa divided by normality. Normality. What is the unit? Siemens centimeter square. Equivalent inverse. EQ inverse. Here mole inverse, there equivalent inverse. Ready? Fine. So if very same time, if kappa given in Siemens meter inverse, then equivalent conductance is equal to 10 to the power minus 3 kappa divided by normality. Fine, very same time. Here molarity. For molar conductance, it is molarity. For equivalent conductance, it is normality. Because mole and molarity are related, equivalence and normality are related. You know the relation. It is already discussed in your redox reaction. So here the unit will be Siemens meter square equivalent inverse. Okay, ready. So that is the difference between molar conductance and equivalent conductance. Okay, so what is the difference? If I have a conductivity cell where 1 mole electrolyte is filled, then the conductance of that all ions which present in 1 mole electrolyte, which is defined as what? Which is defined as molar conductance. Whereas in the very same time, if I have 1 equivalent electrolyte, 1 gram equivalent electrolyte in a conductivity cell, and the all ions of that 1 gram equivalent electrolyte may offer a conductance. That conductance is said to be equivalent conductance. Ready? And your molar conductance, which is related with the molarity, whereas equivalent conductance is related with the normality. Okay, and you know that for a same solution, there is a relation between normality and molarity. Normality equal to molarity in n factor. Normality by molarity is equal to n factor. That relation is also here also. I'll explain. Okay, so first of all, there is a relation between lambda m and lambda E. Before entering to that relation, there is a relation between lambda m and kappa. It is obviously there is a relation because lambda m is a conductivity of a bulk portion, or lambda is a conductivity of bulk portion. And in that bulk portion, we have a specified portion, 1 centimeter cube portion. And the conductance of 1 centimeter cube portion is already defined as kappa. So that 1 centimeter cube kappa conductance may related with the bulk conductance lambda m or lambda E. So that is the relation. Okay, no need of derivation. You simply study this relation. Okay, so there is the point that you have to know that if kappa is in Siemens centimeter inverse, then here is 10 raised to 3 both side. Whereas in the very same time, if kappa is in Siemens meter inverse, here is 10 raised to minus 3 in both side. That you have to memorize. Moreover, in molar conductance, the term is molarity, whereas in equivalent conductance, the term is normality. What is N? N is normality. That is the difference. It is very important. Okay, we'll discuss the problems from this topic. Okay, before that, let me connect the molar conductance and equivalent conductance. Let me connect the molar conductance and equivalent conductance. Ready? So please allow me to connect the both. Molar conductance divided by equivalent conductance. We know that molar conductance is 1000 kappa divided by molarity. whereas equivalent conductance is 1000 kappa divided by normality. So for a same solution, 1000 kappa cancelled. It will be normality divided by molarity, and you know that normality divided by molarity ratio will be the n factor of that particular substance. So the point that you have to note that, let's have a note point. For a same solution, if I have same solution, have a KCl solution, have a HCl solution, NaCl solution, the solution is same. Then what is the relation between the molar conductance of that particular solution with the molar conductance of that equivalent conductance of that very same solution? Is that molar conductance of that solution to the equivalent conductance of that same solution will be equal to n factor. So for a same solution, what is the specialty of a same solution? For a same solution, its conductance, specific conductance is always a constant because the conductance of that particular region is a constant. So kappa is a constant. For a same solution, molar conductance divided by equivalent conductance will be equal to normality divided by molarity of that solution, and it will be equal to n factor. You know what is n factor, I think. I already discussed the term n factor. So these all are the relation. Okay, so these all are the important terms of electrolytic conduction.